In section 5.2, we'll be discussing particle motion. So particle motion problems deal with particles that are usually moving along the x-axis or the y-axis. So we're talking about horizontal or vertical movement. So in this class, we'll only talk about movement that is horizontal or vertical, so moving left and right or up and down. So the position, velocity, or acceleration of a particle's motion are defined by functions, but that doesn't mean that it's moving along the graph of the function. Just the graph represents the position. So it's actually moving along an axis, so either back and forth, left and right, or up and down. So the terms we're going to use will focus on horizontal motion of particles, but just know they apply to vertical motion as well. So some important vocabulary. The first is position. That is where the particle is located at a given time t. So you'll often see this as s of t, x of t, or y of t. So x of t if it's moving horizontally along the x-axis, y of t vertically, and s of t is just kind of a general position equation. Now, velocity itself is how fast position is changing, and so we have two different types of velocity, average velocity and instantaneous velocity. So average velocity is just the average rate of change of position, which means it's the change in position over change in time, or the s of b minus s of a over b minus a formula that we're used to for average rate of change. So it's average rate of change of position, so it's my position function that I'm using in my formula. That would also be the slope of the secant line between the endpoints on my position graph. Instantaneous velocity is the instantaneous rate of change of position at a given time. So notice average velocity is over a time interval. Instantaneous rate of change is at a given time. And that includes the direction of the movement. So what we're talking about there is the sign. So it will be positive or negative, and that will determine the direction. And we'll talk more about that later. And so the way we find velocity v of t, it is the derivative of s of t. So it's s prime or ds dt or the slope of the tangent line to our position graph. Previously, you might have thought about speed and velocity as the same thing, but speed is the rate at which position is changing, but it does not have the direction. So it doesn't have the positive or the negative sign. Well, it's always positive. It won't ever be negative. So what that means is it's the absolute value of velocity, or absolute value of v of t, or you can think of it as the absolute value of ds dt, the derivative of s. So you'll see it in any of those ways. And then finally, acceleration is the rate that velocity is changing. And so again, we have average and instantaneous. Average acceleration is average rate of change of velocity. So notice I'm talking about average acceleration, but I'm using velocity in my equation because it's how my velocity is changing. Instantaneous acceleration is how fast my velocity is changing at a given time. So that is just the derivative of velocity, v prime, or the double derivative of position, since velocity is the first derivative of position. All right, let's go ahead and do an example. So we have a particle's position is given by this function, s of t equals e to the t sine of t, where s of t is measured in centimeters and t is measured in seconds. So those units are going to be important to us. We want to answer these questions now. So the first question says, what is the average velocity on the interval t equals 1 to t equals 3 seconds, and will indicate appropriate units of measure. So my average velocity, I can write that just v sub average. That is equal to, it's the average rate of change of position. So I'm not using the velocity equation here, I'm using position. So I'm going to just use that formula from above, s of 3 minus s of 1 over 3 minus 1. That could give me a point on the AP test, but it's not going to give me full credit. I need to actually evaluate my s function. So this is going to be e cubed times sine of 3 minus e to the first sine of 1 all over 2. And then for the units, pay attention, I had s on top. So I'm going to look at my s units. My s was measured in centimeters. On the bottom, I had time. That was the 3 minus 1, and my time is measured in seconds. So I can actually leave my answer like that. I do not need to simplify any of this. I could put it in my calculator and get a decimal, but we're not going to worry about it. We're going to leave it just like that. So that is our answer here. Now in part B, it asks for instantaneous velocity. So whenever I see instantaneous, that means the derivative. And so the derivative here is what my velocity represents the change of. So that's the derivative of position. So velocity is the derivative of position. And it will ask me to find that at 1.5, but remember I need to find the derivative first before I can evaluate it at 1.5. So I'm going to be taking the derivative of e to the t sine of t. There is a multiplication symbol inside there, so I will have to use product rule. So this is e to the t, that's the derivative of the first part, times sine of t, plus e to the t times the derivative of sine of t, which is cosine t. And it will help us if we can rewrite that as e to the t. I can factor that out, sine of t plus cosine t. Now I'm going to evaluate at 1.5. And so that will just be e to the 1.5 times sine of 1.5 plus cosine of 1.5. Now I do need to put units here. My units will be the same as my average velocity units. And so it's just velocity units will be distance units over time. So in this case, again, centimeters per second. And once again, I can leave my answer right there. I do not need to simplify it. C asks me for average acceleration on the interval from 1 to 3. And so average acceleration is the rate of change of velocity. So velocity at 3 minus velocity at 1 over 3 minus 1. Now this is going to look a little crazy here. I'm just going to evaluate my b of t equation. I'll use a simplified form at 1 and 3. So e to the third times sine of 3 plus cosine 3 minus e to the first times sine of 1 plus cosine 1 all over 2. Now you could probably simplify that in some way, but we're just not going to worry about it. We're not going to spend our time on it. For the units, think about what is in the numerator here versus the denominator. So in the numerator, I had velocity. As we talked about before, my units for velocity were centimeters per second, just kind of like what we had in A and B. But then I'm dividing it by time again, so it's centimeters per second per second, like that. I can leave it like that, or I can simplify it, which we'll talk about in this next problem. So instantaneous acceleration, A of t, that is the derivative of velocity. And on the AP test, if you're introducing this new equation like A of t, I have to relate it back to the old equation. So v prime of t, and then I had already said v of t was s prime of t. So these are all connected back to this equation that was given to me. So I am going to take the derivative now of my b of t equation. That was this e to the t sine of t plus cosine t. Again, I will have to use product rule. So the derivative of e to the t is e to the t times the second part, sine of t plus cosine t, plus e to the t. Now I'm going to take the derivative of the second part. The derivative of sine t is cosine t, minus the derivative of cosine t is, plus the derivative of cosine t, which is minus sine t. Now, if I were to simplify that, I would notice that the e to the t sine of t and the e to the t times negative sine of t would cancel out. And so then what I have is 2 e to the t cosine t. And so when I want to find a of 1.5, my acceleration at 1.5, I can just plug 1.5 into that. Now, it's again okay if you didn't simplify that, you could just write it all out. But one thing I am missing here is units. And so, like we said in C, my units here were centimeters per second, but if I want, I could write that as centimeters per second squared. So acceleration units are always distance over time squared. So we can connect the concepts of position, velocity, and acceleration to all of the function analysis that we did in Unit 4 with the f, f prime, and f double prime. So what we think about is position corresponds to what we thought about as our f graph. Velocity, which was the derivative of position, corresponds with our f prime graph. And acceleration will correspond with our second derivative, f double prime. So all those rules we learned about our f, f prime, f double prime chart, we can use those here, but with position, velocity, and acceleration. So just remember velocity is the derivative of position, acceleration is the derivative of velocity, or the double derivative of position. So in example 2, we're given the position, so I'm going to highlight that, s of t, of a particle which is moving along the x-axis. So this is our position graph. Again, it does not mean that my particle is moving along this graph. It just represents my position. So it'd be like this y value is 3, so I'm at 3, and then 4, and then or maybe 5, and then down at 4, etc. And we'll be working with those more. So this is my graph of s of t. I'm just going to label that again. I know it's written up there, but I want to make sure. And then so when I'm thinking about my velocity equation, that would be the derivative of this graph, and my acceleration would be the second derivative of this graph. So question A says, at which points is the velocity equal to 0? So that means when is s prime equal to 0? In other words, when is the slope of this graph equal to 0? So that's going to be at my horizontal tangents. That will be at B and D. So v of t, my velocity, is equal to 0. Or let's not say when. Let's say at B and D, since S has horizontal tangents. You could also say since S prime equals 0. Those are equivalent statements. B, at which point does the acceleration equal 0? So acceleration equals 0 means when is the second derivative 0? So that will happen when you have inflection points. So when your graph changes from concave up to concave down, or vice versa. So the only place that that happens on this graph is at C. So notice I am concave down, and then at C I switch to concave up. So A of t equals 0 at C, since S of t has an inflection point. C asks, on what intervals is the velocity positive? And so, in other words, when is S of t increasing? So the slope of this graph positive. And so that would be, we're not going to say from negative infinity to a, because usually with time, our time is greater than or equal to 0. We don't usually have negative time. And so we're going to say velocity is positive on the interval from 0 less than t less than b. And because my graph was increasing there, and then also from d, and then we could have up to infinity, d less than t less than infinity. And our justification there is since s of t is increasing. So that's why I know that my s prime, my v of t, is positive. So the particle's velocity was negative on the opposite intervals there. V of t is less than 0 on the interval b less than t less than b, since s of t was decreasing. E asks, on what interval is the particle's acceleration positive? And so that means s of t is concave up. The acceleration is positive means my second derivative is positive. So if we look back up at our graph, we are concave up from c to infinity. So a of t is greater than 0 on c less than t less than infinity, since s of t is concave up. And then for the last one, where is the particle's acceleration negative? Same idea. A of t is less than 0, but we're going to say from 0 less than t less than c, the first part, since s of t is concave down.